Another way of studying this is to record visual evoked potentials. So as you discussed also in one of the first classes, it's possible to record the electrical changes over the visual cortex when you observe a visual image, which is, for instance, blinking. And you can then record these different potentials. One of them is especially interesting. It comes at a latency of about 300 milliseconds, and it has positive deflection, so it's called the P300. And what is interesting there is that it turns out that the size of this P300 is dependent on to what extent the subject is paying attention to the visual stimulus which is there. So if the subject here attends to the left or attends to the right, you see a modulation of the size of this P300. This is useful from a practical point of view. This is the way that people have now developed devices which can be used to communicate actually with people who cannot communicate otherwise. Because what you can imagine is that you can have a computer which blinks different letters in different areas of the screen, and then all the subject has to do is to pay attention to different parts of the computer screen where that letter is that he wants to communicate, and then the P300 will be larger when that coincides, and you can record that, and the computer can decipher that, and you can actually write on a computer just using your P300. So the world record right now is writing 27 letters in a minute, just sitting in front of the computer and paying attention to different blinking letters, and then the computer will record your P300 and write what you want. And that's really being developed more and more these years. So within relatively short time, you will be able to use these devices also for computer games. It's already possible now to play computer games, for instance, where you have to move a virtual ball from one part of the screen to another, and you can sort of compete against another person, and it's all about paying attention and increasing your P300, which can then sort of be used to move the ball to the other person's court and so on. And these kinds of games are becoming more and more popular right now. They're also available for iPhone if you want to, but so things are developing very quickly. Another example of very much the same thing, if you use transcranial magnetic stimulation and evoke motor evoked potentials in two different muscles, here for the thumb or for the little finger, you can actually see that if the subject focuses on one or the other of these muscles, just simply sitting there and focusing on the thumb or focusing on the little finger, you can see that the motor evoked potentials are greatly modulated. So when the subject focuses on muscle 1, the motor evoked potential there becomes much bigger. When he focuses on muscle 2, the motor evoked potential in that muscle becomes much bigger. So you can do very much the same thing also for the motor system and sort of increase the excitability in the motor cortex by focusing on different parts of the body. This has also been investigated in various ways in monkeys to see how monkeys interact with the environment and how that attention improves the reaction of the monkey to a visual stimulus. So in a reaction task where the monkey has to react as quickly as possible, you will see that if the monkey focuses on the stimulus or the area where the stimulus is going to come, the monkey can react much, much more quickly than if it is focusing somewhere else. This is not really surprising. This is shown also in the book, basically that there is coding so that you become much more quickly to react when the visual stimulus is coming in the area that you're expecting it to come. The lowest.
I didn't get it in the book. If the liver is released, I just didn't get it.
Okay, I have to look up on that because I can't remember it right now, but I'll look at it. So basically, we don't know exactly how this is being done. There are ideas, but it's only ideas that parts of the thalamus, to the very dorsal part of the thalamus, the pulvinar nucleus, is involved in sort of orchestrating this regulation of attention. And of course, this would make sense that it would be some kind of a centrally located nucleus closely related to the thalamus, which is basically where you have all the sensory input coming into the brain and being distributed to the different parts of the cortex. So it would make sense to have sort of a regulating filter which can decide which part of the sensory input which is being amplified and sent to the different parts of the cortex and thereby brought to conscious attention. But this is still quite open issue. So basically we don't really know how this process is taking place and how the brain orchestrates this. But in all likelihood, I think looking at the literature now, it's not just one nucleus. The pulvinar definitely has a role in it, but as is also sketched here, it's very likely very many different parts of the brain which takes part in this, and basically so that it's a network which together through the activity in that networks brings different parts of the activity in the brain to our conscious attention. But I think this is also something that Mark is going to come back to in relation to attention, in relation to consciousness later on. Neglect definitely also has something to do with it. So I think you are already familiar with neglect syndrome, the observation that some patients with lesions, in particular the right parietal lobe, do not pay attention to parts of their body or parts of their visual field. So it's not like they cannot see anything, it's just that they ignore it, that it's not part of their consciousness. So also the parietal areas are definitely involved in generating this conscious attention to objects. There are also specific syndromes following parietal lesions, this syndrome called Berlin's syndrome, which is basically that they have problems in doing this ambiguous Stroop kind of test. So they can definitely, when you have objects which are all the same color, they can name that it's red. If they're all the same color here, green, they can name that it's green. But if they're both red and green, they ignore one of them and only pay attention to the red ones as if they didn't see the green ones at all. Now, if you then couple these so that it's a more organized visual input that they get, you just connecting them by a stick here, they recognize both the red and the green simply because now there's less information, so it's more restricted, and then they manage to see it. So it's sort of the, you could say that it's how much information that can be processed, and when they have this lesion, that amount of information is greatly limited. I think that was all I had. So basically, the communication is that we do have this ability. It's an interface between our conscious self and physical activity in the brain, probably through a network involving many of the different nuclei in the sensory systems. So, Jesus, I'm not good at it.